This is the 4-9 notes for Calculus 1. Calculus 1 as a whole is made up of 3 fundamental topics. We start with limits, which we've covered in this class earlier on. Then we move to derivatives, which we basically just wrapped up in the prior section we covered. Matter of fact, it kind of wrapped up both derivatives and limits at the same time with L'Hopital's rule. And then we start at 4-9 right now with the last fundamental topic, and that topic is called antiderivatives. Just like the word states, antiderivatives are basically the reverse of derivatives, the opposite direction, if you will. So worth noting that the variable capital F is often used, at least in this textbook, to represent an antiderivative. So we can define an antiderivative as the following. If the function f is an antiderivative of some other function, little f, then taking the derivative of that antiderivative will lead us back to the function f. So that's pretty much what the definition states, but most students don't get a lot out of that because it's very wordy and kind of strange the way it's written. So the best way to really talk about it is with an example. So let's do that. So let's say here we have the derivative of x squared. We all know that to be 2x. It's one of the easiest derivatives. It's one of the first ones that we did using the power rule. 2 to the front, subtract 1 from the exponent. But the new terminology can actually be applied to this as well. We can say that an antiderivative of the function 2x is capital F of x equals x squared. So if we want to get rid of the f notations, we can just say an antiderivative of 2x is x squared. Okay, so if you think about that for a second, you're like, okay, well, I guess that makes sense. If we know that the derivative of x squared is equal to 2x, then we know that the antiderivative of 2x is x squared. So derivative this way, antiderivative the other way. That's exactly what we're doing, basically. So what you're going to basically have to do from the rest of the course is to mentally go the other direction. That's it. That's going to be the key of what you're going to have to be able to do. But there is one small issue, and you might have noticed, or maybe you didn't. It actually uses the word an antiderivative, not the antiderivative. So by saying an antiderivative, it's implying that there's more than one. So the question is, in this standpoint, is x squared the only antiderivative of 2x? And if you want to think of it from a derivative point of view, you could say, are there any other functions besides x squared that have a derivative of 2x? These two statements mean exactly the same thing. So think about that for a second. Are there any other functions but x squared that you can find the derivative to find 2x? Now, if we were in the classroom, that I would ask and I would wait. And normally, at least 2, 3, sometimes more students will be like, wait a second, this is actually a lot easier question than we would possibly ask, because if you think about it, think about these guys. So isn't x squared plus 1, isn't that derivative 2x? Isn't x squared minus 5, isn't that derivative 2x? So what does that imply? That implies there's an infinite amount of functions that have a derivative of 2x. That is pretty profound. So here's the problem. How do we designate an infinite amount of derivatives? We can't just say, all right, find the antiderivative of 2x. You can't just write x squared and circle it. That's really wrong, right? Because it's only one of them. So how do we symbolize an infinite number of them? That's using this theorem here. It says, let f be an antiderivative of f on some interval. Then all antiderivatives f on that interval have the form f plus c, where c is an arbitrary constant. Okay, so instead of writing just, let's say, x squared, you're going to write as the answer x squared plus c. So anytime you find a straight antiderivative, you need to put plus c on the end of it to signify that any constant could be added and subtracted, and you would still find the same derivative. Okay, so we're going to start slow here. So let's do some mental work. So if you were to look at 1, it says find all antiderivatives of the functions. So if you were to look at the function 4x cubed, if it asks you to find the antiderivative, then you need to think about what function you took the derivative of to get this. Okay, again, I usually get a lot of hits in class where students will be like, oh, wait, so all we have to do is kind of undo the power rule, if that makes any sense. So what the number that went to the outside over here is actually the number that was originally here. So that means, well, what would I have to take the derivative of? Well, x to the 4th. So that's where your thinking is going to have to go, essentially, is knowing that x to the 4th's derivative is 4x cubed and doing that process backward. But this isn't the answer. According to our family of derivatives theorem, we must put plus c at the end of it. So that is the antiderivative of 4x cubed. What about 2? Antiderivative of e to the x. Well, what do we take the derivative to get e to the x? Well, this is sort of a no-duh thing. Well, e to the x's derivative is itself, so its antiderivative is also itself. So we would write e to the x, and then we would have to remember plus c. For the last one, 3. What about cosine? What function do we have to take the derivative to get cosine? Well, sine. But we have to add c, because that's what we get. So just to be clear, if you look at any one of these results that we have here, any one of them that we put here, this guy, this guy, this guy, if you take the derivative of anything in those green boxes, you're going to get back to the original function. So welcome to a huge cheat that now you have on all your exams. You guys already know how to find derivatives. So that means if you get an antiderivative, you can always check your work by just finding the derivative of the antiderivative, and you should end up back at the original function. Okay, so let's get some technical jargon out of the way here. Okay, so basically this is the this guy over here. This is the technical way to write an integral. Okay, so we call this right here the indefinite integral symbol. So right here is the indefinite integral symbol. So it's just, you just draw it. It is what it is. Mine usually looks something like that, just so you know. So it's you'll see it as I go all the way around, but what that says is take the antiderivative. That's exactly what it means. We say a function that follows an integral symbol, indefinite integral symbol, is an integrand. So you're not going to use this term very often, but this is called the integrand. And note that I don't want to skip this, but I did say this was an indefinite integral symbol. Note that we are going to be covering definite integral symbols later. So for now, though, it's indefinite, which means there is nothing that it's between what two values that we're integrating between. So that's next. So integrand is our next. So that function is integrand. And then the last part, which is kind of bizarre to look at, is this right here, dx. So that's called the differential, and the differential, also called the variable of integration, which is x. That basically tells us what to integrate, what symbols. So just like when we did d dx, this variable told us what to take the derivative with respect to. Now this differential is going to tell us what to take the integral with respect to. That is the key in terms of the values. So now, just a side note here, if you look at these equations down here, so these equations are basically 1, 2, and 3, but rewritten with this terminology. So what would we say? We would say that, let me just highlight it as we go here, hold on. So we would say that the integral of 4x cubed dx is equal to x to the fourth plus c. We would say that the integral of e to the x is equal to e to the x plus c. We would say that the integral of cosine x is equal to sine x plus c. So this is the absolute basic way that we would write an integration equation for what we would actually be looking for. And obviously we're going to get into that a lot more as we go, but that's the idea. And just remember, this big C is going to be present in every single antiderivative problem where we have an indefinite integral. Okay, so moving on here. The rest of this section, or most of the rest of this section, is all about equations for finding the antiderivatives of all the popular trig functions. So for derivatives, in the previous chapter that we went through, the previous chapter, we actually took section by section by section to conquer all the individuals' functions' derivatives. So this is different. So now that you know the derivatives, finding the antiderivatives should be much easier. So they actually cover all of the antiderivative formulas in just this section right off the bat here. So what we're going to start with at the top is the power rule for indefinite integrals. So what is this going to do? This is going to be the formula that's going to undo the derivative power rule. So what was the derivative power rule? Remember, just like we said before, the derivative would bring 4 to the front, and then we would subtract 1 from the exponent. So what integral power rule can we use to get back? Well, a lot of you might be like, oh, we just did it in our head. Can't we do that normally? Well, it's a lot harder than you think when it's not just a perfect undoing of something. So you'll see that in a second, but I just wanted to point out that this is going to be that exact rule. Okay, so the rule here is if you take the antiderivative of x to some power, that is always going to be equal to x to the p plus 1, so add 1 to the exponent, over that same exact exponent value, p plus 1 plus c. Okay, this is actually super simple, just like this was and became back then. It's just getting the hang of it as we go. So when we do this, the whole point obviously is to isolate something to just x to a power. Now, but what I want to do before I do an example is I want to prove it to you. I want to prove to you that this formula is true by taking the derivative of the right side and showing that the result is going to be x to the p. Okay, so let's do that. It's going to be a little funky, but let's do it. So here we go. So we're taking, this says take the derivative of the antiderivative. So take the derivative, the little mark there, of the capital F antiderivative. So what are we doing? We're taking d dx of the purple highlighted part right here. So we obviously know that the derivative of a constant is 0. So that's actually just going to essentially disappear from our problem because that's going to become 0. It's not going to be there anymore. So instead, we're going to concentrate on using the power rule in order to find the derivative of that quantity right there. Now, everybody see, so this is x and this is p. Well, p in this problem is just any real number. So it's not a variable, it's basically a constant real number that is not going to be part of the process. What do we do with any constant when we take the derivative? We move it to the front. So basically, we're going to take 1 over p plus 1 to the front of this, and then take the derivative of just x to the p plus 1. Okay, so all we did, it was, right, so by the way, it was under here, right? So we're just moving it out, and because it was in the denominator, we're allowed to do that because multiplication puts us in that situation where that is okay. So what is that going to get us? Well, we're going to get 1 over p plus 1 as a constant, but then what do we can now use the power rule in order to find this. So what's the power rule? We take whatever's in the denominator or in the exponent, we move it to the front, And then, just like we did in that one problem long ago, we have to subtract 1 from the exponent that was already there. So some interesting things happen. Look at this. These two cancel out, and then 1 minus 1 becomes 0, and look at what we get. Look at what we get. Right there. So what that does is that's a proof in which we have proven that this is the proper formula for finding the antiderivative of any power function. Okay, let's do some examples. So what I did was I brought back the equation that we did the mental math for right here. So I wanted to show you how that antiderivative works with the formula so that you can make a connection between what we're doing. So a couple things, though, of importance before we get there. So I should have put this a little bit earlier, but we can just go and refer to it. So it turns out that the rules that apply to derivatives in terms of multiples and sums, and differences, by the way, are exactly the same as for antiderivatives. For example, if you have a constant, which is right here, times a function, and you take the antiderivative, you can move the constant outside and then take the antiderivative of the function itself. Just like if you have the antiderivative of the sum of two functions, you're allowed to take the antiderivative of them separately. Okay? So this one is going to be helpful for what we do up here, whereas this one is going to be helpful for what we do, or both are going to be helpful for what we do down there. So let's take a look at our first problem here. So if we have the integral of 4x cubed, what do? So when we actually take the integral, in other words, take the antiderivative, we can drop that symbol and the dx, and we can write what the antiderivative is. But what we're going to do first is we're going to take the constant out and get this. Okay, so basically what we're doing is we're using this rule right here. So we're taking the 4 out and saying it's a constant multiple, so it's basically, again, going to go along for the ride. Okay, so the 4 stays. Now we can drop the integral and the dx as we actually take the antiderivative with respect to x. What is it? Well, we got to employ this formula. So what is p right now? What is p? It looks like that is 3. So what do we do with that? We do x to the 3 plus 1, and then all we do is copy that same value in the denominator, and then we have to remember the plus c. If we do the math, we get 4 times x to the 4th over 4 plus c, and then the multiples cancel, and we get just x to the 4th plus c, and that is our antiderivative. So again, look what we ended up with, right? X to the 4th plus c, same exact thing, but we're using the formula that we're basically having. Now, you might notice there is definitely a big logic to this formula. Basically, if whatever this constant is basically there to undo the constant in the original formula, which was kind of made in the proof. Basically, this is here to undo the constant that you generate when you take the 4 and move it to the front, let's say. So that's why this formula actually works really well with what we're doing. So we get that. So let's go to 5 so you can see when mentally it's not always that easy to do. So first step, take the constant out. It's going to go for long for the ride. So we got 10, we bring that down. So over here we're going to do, this is x to the p again, but 2 is p this time. When we take the antiderivative with respect to x, which is what this dx says, we can drop the symbolism and just do the antiderivative. Well, what is the antiderivative of x squared? Well, it is going to be x to the 2 plus 1 over 2 plus 1. And then we have to have a plus c. So we're going to get 10 times x cubed over 3 plus c, which means it's 10/3 x cubed plus c is going to be our antiderivative. So you'll probably see here that this isn't as easy a mental process as you would think, because we're not always going to have a perfect antiderivative that's there. So no single function without a constant is going to create 10x squared. Instead, we're going to have this 10/3, which is going to generate the 10x, the formula that we need in order to create it. All right, so again, let's keep on moving through these and doing antiderivative formulas. So now, as I said before, both of these are going to help us do these two problems. Why? Because this is going to be all about sums and differences. So just like we took these types of problems when we were working on all types of, let's say, derivative problems, now we're going to do the same thing for antiderivatives. So if you look at number 6, you'll see that I have the antiderivative of the product of w squared plus 1, 2w minus 5, dw. Okay, so note, do you see how the variable changed, which means your variable of integration changed? Note, that always has to be there, by the way. A lot of students will just ignore this, especially when they first learn about it. You cannot ignore that. If there's an integral symbol, there must be a d with a variable that you're using. It has to be there. If it's not, you're going to get points off, FYI. So, some of you might look at this problem and think, oh, geez, like it's a product. Is there some type of like inverse product rule or reverse product rule? We'll get to all that stuff later and the things that we can undo. But for now, we can just make this problem much easier by just foiling. So, for example, if we bring this down and say, let's take the antiderivative of this expression, we can just FOIL it first. So what do? We get 2w cubed for our first term. It looks like our outside term is negative 5w squared, inside 2w, and last negative 5. Bring down the dw. So now what we have is a polynomial. Just like we could find the derivative easily of a polynomial, we can find the antiderivative easily of a polynomial. So I'm going to write all this out because I want to show you how the rules work. But realize eventually you're going to be doing this very quickly and in your head. So according to this, if we have the sum and difference of a bunch of functions, we can pull them apart so they're individual. So how would you do that? Well, I'm going to skip a step here. So remember, the 2 can come out, integral w cubed dw. Then bring down the minus. The 5 comes out, integral w squared dw. Plus 2 comes out, w dw. Minus 5 comes out, and then just dw. Nothing else is in there. Okay, so like I said, you're probably not going to write this. I mean, when you do derivatives, do you actually write out ddx of every term? No. You've known it well now that you're going to go through and do it quickly. So same thing goes here. I'm just doing this in the beginning so everybody's clear on what they need to do. So what I want to do now is I want to make this process faster. This and this. So instead of doing this plus 1 over plus 1, like written out, let's just do it mentally. That's what you want to get to, and that's how I'm going to do it. So what is the antiderivative of w cubed? So what do? You add 1 to the exponent, copy the exponent below it. Done. Now normally we put a plus c. It turns out that when you do a bunch of terms like this, all we need is a plus c at the end of all the work that we do. We do not need to write a plus c after every individual term, because all we need is a plus c at the end to take care of the one constant, type of constant that could come at the end. So we just move on. So the 5. What about the antiderivative of w squared? Well, w2, add an exponent, 1 to the exponent, and then copy the exponent underneath. Again, 2 stays put. Add 1 to the exponent, 2 underneath. Here, 5. What do? Well, it's kind of an interesting dynamic of what we have here, because there basically isn't a variable. So think about this for a second. If it was w cubed, w squared, w to the 1, then what hypothetically is sitting here that we don't see? W to the 0. So if we need to integrate w to the 0, we get w to the 1 over 1. In other words, just w. And then we must add c on for our constant. Okay, so it's a couple notes before we simplify. So if you pay attention to this right here and this. So whenever you take the antiderivative of a constant, all you're going to have to do is tag a single variable onto it. Why is that? Because when you take the derivative of this, what happens? You just end up with what's in front, -5. So it's the reverse concept of what you have to do. So be aware of that when you're going through the problems, that that's something that's very simple that you can do without a problem. So the rest of this is just simplification. So w to the 4th over 2, when we simplify the 2 and the 4, this doesn't simplify. So we can get 5/3 w cubed, or 5w cubed over 3. It doesn't really matter. Let's do, yeah, we just do w cubed, that's fine. The 2's here cancel, so we just get w squared. The 5w, nothing happens, and the plus c. So what is the antiderivative of this function? It is this function right here. W to the 4th over 2 minus 5/3 w cubed plus 5w squared minus 5w plus c. Now, as I stated before, when you're done, realize all you have to do is find the derivative of this to check your work. If you're on an exam, why not? Unless you have no time at the end, why not check all your work by finding the very easy derivatives that you already know how to do? Okay, you might recall when you learned about derivatives, I brought in the funky exponents, the ones that are going to cause issues for everybody. So I'm going to do that now. This one's just large exponent. This one, we have it in the denominator, which means you should know what to do with that, which we'll talk about in a second. And this is a radical, which again, you should know what to do with. But why don't we just separate it into pieces first? So again, we have a constant 4, which means we have to take the antiderivative of x to the 19th dx. Okay, x to the 19th dx. And then we're going to subtract 5 as a constant. It would be 1 over x to the 8th, but everybody should know that that's x to the -8 dx. And then this one does not have a constant for the first time here. And what do we know about radicals? We can change them into fractional exponents. So x to the 1/2 dx. Okay, so this is basically what we're going to do is we're going to use, again, the power rule for integrals, but now we're going to use it in some of these very funky ways all the way through. So here we go, mental math for some of it. X to the 19th becomes x to the 20th over 20. That should be starting to get routine at this point. What about here? 5 becomes, and this is tricky, so x to the -8 becomes x to the negative what? So we have to add 1, which means we're going to get -7 over -7. So even there's a negative, you have to copy the negative into the denominator when you do that. Minus, what about x to the 1/2? Well, I'm going to do an aside over here. We're going to get x to the 1/2 plus 1 over 1/2 plus 1. So what is 1/2 plus 1? It's 3/2. So we're going to get x to the 3/2 over 3/2. And then since we're at the end, we have to put a plus c. Okay, we've got to simplify. 4 and 20 simplifies to a 5. What about this guy? So be careful here. So it looks like the negatives that occur here and here are going to make this positive. The 5 is in the numerator, and the 7 is in the denominator. The x to the -7 moves down to the denominator and becomes x to the +7. Minus, we have an x to the 3/2 in the numerator, but we can't leave a fraction in a fraction. Oldest rule in the book. So if we are dividing by a fraction, we're multiplying by its reciprocal, which means we're going to get 2/3 x to the 3/2 plus c. So I am okay with you leaving it just like this as your result. Some students, or sometimes you might think about doing, let's say, the square root. Actually, you wouldn't write the square root. Root x cubed or something like that. You could write that if you wanted to, but the way it is right now is fine in terms of the way I would want you to write it. Okay, so I'm just going to add a problem in here in between pages here. So I'm just going to call this, let's say, 7b. If you want to just add it to your notes, I figured why not. Let's do another example just like this one. since this sometimes can be a little tricky for students. So let's say I gave you this. Something that looks like that, all right? So let's say we want to find the antiderivative of this. So what's that going to be? That's going to be 8 x to the 4th dx as we do it, and we would have to do minus 3 is a constant. We would have to do x to the negative 2 dx, and then we would have to do minus no constant x to the 1/3 dx for our problem that we're going through. So if we want to take these antiderivatives, what would we do? We would do 8x to the 5th over 5 minus 3x to the what? Add 1, -1 over -1, right? Minus x to the, well, we did this as an aside before, so it's going to be x to the 1/3 plus 1 over 1/3 plus 1. 1/3 plus 1 is 1/3 plus 3/3, which is 4/3, all over the same number, 4/3 plus c. Okay, the only thing left to do is to simplify. What do we get? We get 8/5 x to the 5th. We get, remember these minuses become plus, so we get plus 3. And then the x goes to the denominator, so we get 3 over x. And then we get, remember this 4/3 becomes 3/4 in the front, x to the 4/3 plus c. So that would be the result. So a little bit of an extra problem, just in case you want it. If you don't need it, you don't need it, and that's okay. Next up in our antiderivative exploration is trig functions. So remember when you take the derivative of, let's say, sine, you get cosine. Now, these trig antiderivative formulas are actually just, they take into account a little bit of the chain rule. Okay, so just to be clear, that's why I'm starting with sine, cosine. So if I had, let's say, the derivative of sine 2x, then that would be equal to the cosine 2x times the derivative of the inner function 2x, which would end up being 2 cosine 2x, right? So basically, what does that mean in terms of this unit? It would mean that the antiderivative of 2 cosine 2x is sine 2x. So these formulas actually kind of take that into account. So notice for the first value, right, this first one, let me highlight it. So we have cosine ax, so a is obviously a constant. So if this 2 right here is not present, which it isn't here, that means if I need to go back to sine 2x, then I have to have a 1/2 present in order to make this actually work. So hopefully you see that because basically the chain rule creates that constant in the front. So if I'm just finding the antiderivative just this, then there's got to be a 1/2 somewhere over here that's going to end up making this work. So that's actually where these formulas come from. For example, if you want to take the cosine of ax, the antiderivative of that, then that is always going to be 1 over the a, which is right here, sine ax. Just like if you want to do the antiderivative of secant squared. Well, how do we get secant squared? We took the derivative of tangent. But if we incorporate the whole a business into that, where there's a constant in front of the variable, we need, again, a 1 over a in the beginning in order to undo the chain rule that we would have used to get there. So we do the same thing with all of these. So you'll notice that the left side of all of these are all the derivatives of the trig functions, right? With the exception of these guys, where the derivatives actually would have a negative sign. So, for example, the derivative of cosine is negative sign. The derivative of cotangent is negative cosecant squared. So how do we make up for that? Well, in the antiderivative of the ones on the right, there's going to be a negative sign on them. So basically, again, these are formulas that you're going to need to know, and your knowledge, of course, of your derivatives is going to help you with that because it's just going backwards. All right, so why don't we just go through some examples to make sure all is good. So a lot of this I do as sort of a mental procedure, I guess is the best way to put it. Like instead of memorizing these, like I don't memorize these. I just have a structure in my head on derivatives, basically. So everything's from the derivative point of view. So the antiderivative of cosine 2x dx. Well, we know that a is 2, right? So the question is, if I take the antiderivative of cosine, then do I get sine or do I get negative sine? Well, how did I get to cosine in the first place? I took the derivative of just sine. So therefore, this has to be a positive sign. So what do? I do 1 over my a, which is 2, and I do sine ax, which is 2x, plus c, and I am done. Now again, what would happen if I wanted to check my work? I would just find the derivative of this, but look, let me get rid of some of the noise here. So all the extra stuff I did. So what happened when I took the derivative up here of this? I got 2 cosine 2x. And if I multiply that by this half, what do I get? I end up back at cosine 2x. So hopefully when you look at this, you can see how these formulas work and why they're actually formulas other than just memorizing them, because that is actually how it all comes together. All right, number 9. So what about the antiderivative of secant squared 6z? Okay, so when I look at secant squared, I immediately say in my head, I get secant squared by taking the derivative of tangent. No negatives involved, which means that the antiderivative is indeed just going to be tangent. But a in this problem is 6, so that means I have to do a 1/6 on the outside. I have to do a 6z here and a plus c, and I am complete. That is my antiderivative. That is how I think about it. I don't even look up here. I know I'm the math professor, but like even back to when I was in school, I purposely didn't memorize these other than knowing there's a 1 over a in there. I structure them as in I know my derivatives so well that I just undo them, and that's where I come with the formulas. Now, can you memorize? Sure, but I'm just telling you the way I do it. Okay, what about number 10 over here? So sine of x over 2. So this can be a little tricky. Again, I've said this before earlier in the classes. So what is a in this problem? Well, when students look at this, their brains sometimes get a little burned up. So remember, when you see x over 2, all that is 1/2 x, which means our a in this problem is indeed just 1/2. So make sure you're always prepared with that. Now, what about the antiderivative? So if I want to find sine by taking a derivative, hopefully you understand there's no way to do that directly. So unlike when I take sine to get cosine, when I take the derivative of cosine, I get negative sine, which means if I need to go back, I must have a negative on here to undo that. And then again, 1 over, what's a? 1/2 cosine. And then we just rewrite x over 2 here plus c. Now, note here, we can't leave a fraction within a fraction, right? This can't leave a fraction in a fraction. So if we do 1 divided by a half, divide by a fraction, multiply by a reciprocal, you're going to get negative 2 cosine x over 2 plus c, and that will be your antiderivative. Okay, so we got our last mini example here. So cosecant cotangent. So can you find the derivative of anything that's actually going to get you to cosecant cotangent directly? No. If you find the derivative of cosecant, you'll get negative cosecant cotangent. So in that case, we know that there must be a negative plopped onto this. 1 over whatever a is, cosecant of ax. Well, what is a? Well, there are two versions of it here, 4. So we're going to put 4 here and 4 here, and then plus c. No simplifying needed. This is going to be your antiderivative. And you have to be pretty quick with this. And part of the problem with calculus, more than any other math class that you take, is it's just a revolving wheel. Like, you accumulate topics, and if you don't know your derivatives, doing these antiderivatives is just going to be a punch in the gut. Like, it's really hard to be able to move on without knowing your derivatives inside and out. Okay, moving on to the next group of functions. How about exponentials and logarithms? So in the sections on derivatives, we learned about b to the x and e to the x. And in the section on logarithms, we learned about log base b x and natural log of x. So for the purposes of the antiderivatives for this class, we're going to concentrate more on just the most popular ones, which are e to the x and natural log of x. The other ones exist. You can look them up. They have their own formulas, but they come up so infrequently that I usually stick just to these two formulas that are here. So what does this look like? So the first one is e to the ax. So what does this undo? This basically undoes the e to the kx shortcut formula, which the derivative ends up being k e to the kx. Well, think of k as now a. And the idea is when this k ends up here, we have to undo that. So if we take the antiderivative of e to the ax, we're going to have to do it just like we did up here in these formulas. We're going to have to do 1 over a e to the ax plus c. So let's do an example. So if we have e to the 3x, that means the antiderivative is going to be 1 over our a, which is 3, e to the 3x plus c. Super simple. Quick. No problem. Now, again, if you want to prove this to yourself, then what would you do? You would take the derivative of this entire boxed quantity. Obviously, c is 0 when you take derivative, but this would be a constant over here, and you would do e to the 3k's derivative is 3, or 3x, would be 3e to the 3x, which you would multiply this by this 1/3, and you'd be right back to e to the 3x as your result. So every antiderivative you take, you can basically prove by simply just taking the derivative of your answer. Okay, what about 13? So a little bit different. So since there's a constant in front, what we're going to do is we're going to go by sort of the letter of the law here. We're going to move it out to the front, and note that our variable of interest is t in this problem, so it's changed a little bit. So I did this, by the way, because in a lot of the business financial models, things like that, it's over time. So t with exponentials actually comes up a lot. So what do we get? Well, the 5 stays put. We have to do, our a in this problem is actually -10. So that means we have to follow the formula and say, okay, the antiderivative is 1 over -10 e to the -10t plus c. If we simplify that, we're going to get -1/2 e to the -10t plus c, and that is your result. Now, small note here. So normally when we have negative exponents, we move them to the denominator. When it's an an exponential, we don't. I know that's kind of inconsistent, but there's a reason for that, because if you recall from just algebra and trig, when you have something like this versus something like this is exponential growth, and this is exponential decay. So these are legitimate functions that we don't want to move anywhere. Plus, there's a variable on it too, which makes it doesn't really matter, but it just makes it so that we want to leave them the way they are. So don't move them anywhere. This is good as the answer. Okay, so the last problem concentrates on our formula up here. So if we take the derivative of the natural log of x, review, that gives us the base function 1 over x. Okay, so it makes sense, just watch this real quick, if we want to take the antiderivative 1 over dx, then that's going to bring us back to the natural log of x. But we have to be careful, because in the scope of this number could be positive or negative, but natural logs only take in positive numbers, so we have to force this to be an absolute value, and of course we would get plus c after it. So the logic of the formula makes a lot of sense. Now, don't be alarmed by this. So the dx is only moved to the numerator because there's a 1 there. So in reality, these two quantities are exactly the same thing. If you're more comfortable with leaving dx where it goes and just writing this, I'm fine with that. There's no issue there. So, but this is the form you're going to use. Now note, this one is a little bit of a tough one for students to recognize, and I will show that to you in 1 second after this problem is complete. So how would we do this? Well, if you look at this problem right now, it looks like we have a constant of 2/3 that needs to come out. So we get 1 over y dy. As soon as you see 1 over any y to the 1 power, that is automatically the natural log as its antiderivative. It's just something that you absolutely must be able to locate. So what does that look like? Well, the antiderivative of 1 over y, which is basically this, is the natural log of the absolute value of that variable, which is y, plus c, which you end up with this as your result. Okay, so I want to do an aside here, so hold on a second. So I'm going to do a side down here. So if you want to, again, do like 14b. So if I did the antiderivative of 2 over 3y squared dy. Okay, this is why students will struggle with this versus this. Okay, so if you look at this, the same first step happens and you get 2/3 1 over y squared this time dy. So there's a huge difference between 1 over y and 1 over y squared. 1 over y creates the natural log. 1 over y squared changes to this. And then you take the antiderivative using the power rule. Okay, this is a power scenario. So just for argument's sake, what would that look like? It would be 2/3 times y to the -1 over -1 plus c. You would end up with, it looks like negative, then you would get 2 over 3y plus c. So the y would go to the bottom, the -3 would stay, the 2 would be on the top, and that would be your result, right? Vastly different, has nothing to do with the natural log. So I show this to students all the time in class. I don't put it on here, usually I forget, just because it's not part of the section. And you might want to note that this is not from the section. But I want to put it in there because that is a big issue that students have. You must be able to locate 1 over a single x or y or any variable as the natural log. But if you're 1 over y to or x to a power other than 1, 2, 5, -7, whatever it is, then you're locked into the power rule and you must be able to use that. Okay, we've covered almost all of the functions for antiderivatives except for everybody's favorite, the inverse trig functions. So now, what do? Well, we start out and we talk about the crazy formulas. So just like with our derivative formulas in the other direction, basically we had very odd-looking, fraction radicals, all types of things whenever we took the derivative of an inverse trig function. So we now have to go back. But we're also, just like we did with the e and the trig functions, we're going to incorporate that variable a that helps us determine where some of these variables are going to go. And it sort of does, again, it helps undo some of the rules or derivative rules we had before. Now, for the purposes of what we're going to do, we're only going to concentrate on 3 of the inverse trig functions for what we do, specifically sine inverse, tangent inverse, and secant inverse. The most popular one and the one you have to get very used to seeing is similar to the derivatives. It's going to be this one. So in Calc 2, you're going to have to take lots of antiderivatives, and the inverse tangent comes up a lot. So make sure that that is really the one that you want to memorize for what you're doing. But the other ones are, we'll do practice problems and make sure all is good with them. Okay, so the first one, basically 15, it says antiderivative of dx over the square root of 16 minus x squared. Note, this is equivalent to the dx being here and a 1 being in the numerator. Just like natural log, it's the same thing. It just so happens that they do this shortcut so the dx is not floating by itself. So again, what is this the same as? This is the same as 1 over the square root of 16 minus x squared dx. These two are the same thing. So just to be clear though, what is the idea when it comes to this? So if you see the square root of a difference of two squares in your denominator, then normally that's going to be a sine inverse antiderivative. I'm not going to get too funky or tricky with you when it comes to that. It's just a matter of locating that and recognize that it's going to be sine inverse. So what does that look like? So it appears that in order to find this result, the only thing we need to know is A. So we need to go and change our problem here so that we get, I'm not even going to include this, so I'm just going to highlight it over here. So just note that this is true, but I'm not going to include it in the calculation. So dx square root, we need to find A. Well, this, if minus x squared is over here, right here, then a squared represents this right here. So we're going to change it into 4 squared minus x squared. Hold on, let me try again. There we go. X squared. So this is essentially where we stick with. So that makes a 4. So we can immediately just go right to the antiderivative formula and say x over 4 plus c, and believe it or not, that's it. That is your formula. So not a lot of work. It's just about locating, first of all, which one of these it's going to be, sine, tangent, or secant. Once you know that, then it's about identifying what A is going to be. So these are the easier inverse trig problems. I'll get to the other ones in a second. So what about 16? So if you look at this one, again, this is a radical one. Note that only sine and secant inverse have radicals. But this one has a single x on the outside, which means this has to be our secant inverse problem. So what do we want to do? We need to find the value of A, basically. So we've basically switched up things. So now it's going to be x squared minus a squared. So that means that if we rewrite this, we're going to get 2 over x square root of x squared minus 10 squared dx. Now, interestingly enough, this 2 right here is a constant. So if we were to be smart about it, right in the beginning here, we probably remove that 2 and put it on the outside as a constant, which means that the 2 would stay. And now we have exactly what we need to match this, with a being 10. So what would that be? It would be 1 over whatever a is, which is 2, which is 10, which is 10. And then you would get secant inverse of the absolute value of x over 10 again, plus c. So all I'm doing is using this formula. So note, this needs to be simplified, so we're going to get 1/5 secant inverse x over 10 plus c. Now you might have noticed here, and probably while you were doing it, was that for the first formula, there is no 1 over a. So strangely enough, that's the way all of the work works, is there is no 1 over a going on there. So this does not happen, whereas in the other ones, there is a 1 over a. I should have mentioned that before, but you might have noticed as you went through there is a difference in the formula, which isn't fun, to be honest with you. Normally on exams, I usually stick with giving problems that have to do with just tangent inverse, mainly because that's the one you see moving forward, so it makes sense to test on that one most often. Okay, so there are some trickier inverse trig problems that we need to cover. And it can be a little bit of a challenge for students to get this. But what I want to point out very clearly when it comes to these trig formulas that are up here, let me get rid of all this, is that the x squareds in these trig formulas, inverse trig formulas right here, they have a value of 1 in front of them. The constant is 1, which means you can only use these formulas if that is the case. So the question is, what if you get a problem like 17 or 18 where the coefficients aren't 1? Now that can be a very different story. So that would create a scenario where we would need some other method in order to do this. Now it's not anything like crazy, it's just about being smart with your algebra to manufacture a quantity in which the coefficient is 1 in front of the x squared. Okay, so let's try that. Let's try manufacturing a scenario where there is a 1 in front of the x squared. So dx, start here. So the question is what value would you need to, let's say, factor out of this quantity here in order to make that value in front of the x squared be a 1? Well, most students would look at it and be, well, we have to take out a 9. But then they'll say, but wait, 4 is not divisible with 9. Well, that actually doesn't matter. I know you're used to doing that in algebra, but we can still take something out if it's not divisible by. It just creates an awful looking problem. So what do I mean by that? So if we take out a 9 out of this denominator, we are going to get plus x squared right here. But what are we going to get over here if we're taking out a 9? So this is not always easy for students to see. So what I say is, instead, if we needed to distribute this 9 to get back to here, then what would this have to be in order for it to become a 4? Hopefully you see that it would have to be a 4/9 in order for that to happen. So this is actually a legal maneuver which just so happen has given us a coefficient in front of the x squared of 1. Now, here's the other part of this. Now, what would this actually match to? Well, first of all, before we do anything, this 9 right here is now a constant. So we're going to move it on the outside, and we're going to get dx over 4/9 plus x squared. Okay, so what trig function does this now match to? So we go up here and we go, well, the only one that's not a radical is tangent inverse. So we have a match, basically. So in order to identify A, we have to go to the one that's not x squared and find the perfect square that goes into it. So what's 1/9? Well, 1/9 on the outside. Now, what is 4/9? What value squared gets you that? Well, the square root of 4/9, which is 2/3, which means this is now our value of A. So we now need to return to our formulas, keep the 1/9 here, and then find the antiderivative. So what is the formula? It is 1 over A, so it's going to be 1 over our 2/3 tangent inverse of x over A, so x over 2/3 plus C. Okay, that's the way we start. Now, there's a lot of work to be done here. So normally we, do a reciprocal deal here, but actually we have a shortcut. So we can multiply the numerators and denominators, and 2/3 of 9 is 6. So this is actually 1/6 tangent inverse. We can't leave this fraction here, so we take the reciprocal and get 3/2 x plus c, which is going to be the result of our problem. So as you can see, the skill level of this one went up drastically. So be ready for something like that. This is a calc class. These are incredibly easy if you know the formulas. So something like this might be more appropriate for a test problem because it at least makes you put a little thought into what you're doing for getting the result. Okay, so again, same type of concept. So the 25 here is not 1. So what do we need to do is we need to do the same process and we need to take out the 25. So let's take out the 10 right in the beginning here. So we're going to get, looks like dx will move to the top like we have been. So we're going to get the square root in here, right? We're going to leave it the way it is, but we need to take out a 25 from our quantity so that we get minus x squared here. So what does that mean has to go in this quantity right here? What fraction has to go there? So if I distributed, I would get a 1 right here. Well, that would be 1/25 would be that value I need. All right? So this is a little bit different. So remember this 9 that we took out right here? So this 9 we could immediately move out. The thing is, this 25 that's sitting here in the expression is actually root 25. So what we need to do is, in another step, this is going to be 10. It's going to be dx. Root 25 comes out, becomes 5, and we still have 1/25 minus x squared in the radical. A lot of algebra manipulation students sometimes struggle with, worth noting. So it's very important that you pay very close attention to what's going on here. So now this 1/5 can come out, right? We're going to get dx, but let's change this radical so that we get this, whatever 1/25 we get 1/5 squared in order to get that. So now this is in the value where this is going to be a. So we go to our sign and we go, hey, this is the one where we don't need a 1/a in the beginning. So what do we get? Well, we do our math here. We get 2. We go right to the sign inverse because remember, no 1/a for sine inverse. Okay? We go right to the sine inverse, and it's going to be x over whatever a is, which is 1/5 plus c. So then we can get 2 sine inverse. We invert the 1/5 and get 5x plus c as our result for this problem. So very different, something you want to practice, obviously, but these are how inverse trig antiderivatives work. Okay, so the last page of the notes here tackles on possibly a familiar topic to you, or something you've heard before, called differential equations. Now, differential equations are basically, they're equations with an unknown function and its derivatives, basically. That's the definition of it. But you'll tackle differential equations briefly in Calc 2, and there's an entire class called differential equations at the college. And by the way, it's abbreviated DiffEQ. Okay, for those of you. Those of you who are engineering that are taking this class, you are very familiar with this class on your future schedule because it's very important. But we're just doing a brief introduction to it using a very interesting problem called an initial value problem. Initial value problem, right? And what are these initial value problems? They have both the differential equation, which is just a derivative basically, and then they have some initial condition. And what that ends up happening for us is it allows us to find the exact antiderivative of something, because just to be clear, because of this plus c, every answer that we provide in all these problems, it's actually an infinite answer, because we're getting, this c could be anything, which means any number of answers you can get, whereas in initial value problems, we're actually going to end up with the exact antiderivative because of this, what's called the initial condition. Okay, so what's the logic of this problem? Now, they give you a derivative, which we call differential equation, and they give you an initial condition, which we label. Now, look at the initial condition. It says f of 1 is 1/3. So in other words, if we plug 1 into the original function, we would get 1/3. Well, that's fantastic. We actually have an x and a y, essentially. Here's the issue. Over here, we don't have the original function, we have the derivative. So the question is how do we get the original function? Well, if you have the derivative, then how do you get back to the original function? You take the antiderivative of that function, making sure to, I'm ahead of myself here, making sure to put in the variable of integration. So this is the first step in an initial value problem. So what's weird about this, in every other problem that you've done so far, you were given this entire antiderivative or indefinite integral. Now you have to write it right here. So you have to be ready for this. You have to say, all right, how do I write it? I write the antiderivative of whatever the differential equation is, or in other words, the derivative, and then I put the d and then the variable that I'm using. Be ready for that. So once I do this, I can actually go to work. I can, without any problems. Now this is returning to the beginning of the lesson when we were talking about just basic, if you're given one of these guys, right? You can go right through and do every single antiderivative individually because it's separated by pluses and minuses. So that's what we're going to do, but we're not going to write it out this time. We're literally just going to take the derivative as we go. So look at the antiderivative of x squared. What is it? It's x to the 1 higher, 3, over the same number 3. Then we go to 2x and we go, all right, there's a constant of 2. What's the antiderivative of x? Well, it's x to the 1, right? So the antiderivative is x to the 2. Bring down the 2, and then we have to put a plus c on it when we're done. So I'm going to bring this f of x down with us. The only thing left to do is just to simplify. So why don't we leave it as x3 over 3. The 2's actually wipe out, and we get just minus x squared plus c. Okay, so basically, this is our family of antiderivatives for this problem, which basically means this function has a family that looks like this. So it's going to be x cubed over 3 minus x squared plus something, some constant. That's what this is right now. But because of this initial condition over here, it allows us to actually find c. Okay, that is the key to these problems. We can now find c. How do we do that? Well, first of all, of these two values right here, this one and this one, which one is x and which one is y? So I asked this in class, and I'm always it's always humorous to see the students students muff this up, just because it is basic algebra. For whatever reason, because the 1 is on the left side, students say, oh, it's y. No. The x is what's inside the function, and whatever the answer is essentially y, or f of x. So that means if you look at what I have here, I know that x is 1. So look where the x's are in my problem. And I know that f of x is 1/3, which is over here, which means I can right away just start plugging in values. So 1/3, which is f of x, is equal to 1 cubed over 3 minus 1 squared plus c. If I do all of this math, I'm basically going to end up with something very simple. It's going to end up being 1/3 equals 1/3. Those will subtract each other out, and you'll get c. When you add 1 to the other side, you're going to get c is equal to 1. So that doesn't mean you're done. What is the answer to an initial value problem? It is essentially this equation right here, but with c replaced by what you know it is. So the answer to this problem is f of x. Just copy the whole equation that you wrote in that arrow step all the way down, plus whatever the number is that you found for c. So therefore, the answer is x cubed over 3 minus x squared plus 1. So what does that mean as a whole? So this is the only function that will create this derivative when f of 1 is equal to 1/3. That is what that means. That is what you have to make sure you understand. Okay, let's try another one. So this one's going to be a little trickier because there's trig involved. So solve the initial value problem ds dt equals cosine t plus sine t with s of pi equal to 1. Okay, so just to make things a little bit more simple here, remember s of t is the same as ds dt, s prime of st. So actually I'll write it above it so that it's a little away from the problem. So this is the same thing as that. So when you say take the derivative of s with respect to t, that's literally exactly the same as s prime of t. Okay, so that makes a lot of sense here because right now this is like an s of t situation. So the only way to get to s of t is to take the antiderivative of s prime of t. So s prime of t is this function right here. So I want to find s of t. I need to take the antiderivative of cosine t minus sine t. Is it plus? It's plus. Sine t. D what? Hopefully you wrote dt. Okay, you have to remember that. So students, when they do these problems, they completely don't even write these expressions right here. These guys, don't forget them. They're just as important. They have to be there. In the next section, I'll kind of show you why, but they have to be there. They're part of the process. So just a note on this, the formulas that we learned for the antiderivatives of trig functions had a's in them, right? So we had to do 1 over a. Well, what happens when a is 1? All we do is get 1 over 1 here, which does nothing. Which means, in a sense, if we don't have an a, if a is 1 in any one of these antiderivatives problem, we can basically just ignore it, the 1 over a part, and just do the trig. And that's what we're going to do here in this problem. So, what do we do when we find this antiderivative? Well, what is the antiderivative of cosine? Well, what do we have to find? Can we find the derivative of some function to get cosine directly? We can. It's sine, because the derivative of sine is cosine. Now, what about sine t? Can we find sine t directly with a derivative? No. Why? Because the derivative of cosine is negative sine, which means if I'm going to take the antiderivative of sine, I have to take the negative root and do negative cosine t, and then we're going to get plus c as a result. And just to review, remember, a is 1 in both of these. So that means each one of these technically has a 1 over 1 in front of them. But why do that when we don't have to? We'll just get this as our result. Okay, so unlike last time, there's not really any simplifying to do. We can go right to using this. So remember, be careful here. This is going to be our value of t, and this is going to be our value of s of t. So we're going to get 1 is equal to the sine of pi minus the cosine of pi plus c. So I'm going to put parentheses here to show that I subbed pi into the equation. So just a reminder, so on the unit circle, pi is located here at negative 1, 0. So the sine is always going to be the y coordinate, so we're going to get 0 here. And the x is always going to be the cosine. Cosine is always going to be the x. So we're going to get this. So if we solve this, we're actually going to get c is 0, interestingly enough. So what does that mean in terms of the resulting function, s of t, that we're trying to find? That means we're going to copy our equation that we came up with, sine t minus cosine t, but it's going to be basically plus 0, which we don't have to actually write. So therefore, the answer to the problem is just sine t minus cosine t. So interestingly enough, we can sort of apply this whole concept of initial value problems to velocity and acceleration. So a little bit of a blast from the past. Remember, we tackled that, I think it's in section 3.6, don't quote me on that, but we tackled that way back when we were dealing with derivatives. So now, you know, what is the concept when it comes to antiderivatives? So just as a reminder, remember our flow chart of derivatives was position, to velocity to acceleration. Okay, so this was basically derivatives. So take the derivative of position to get to velocity, take the derivative of velocity to get to acceleration. But wouldn't it make sense that we can go backwards too? So what if we have the acceleration? Can't we take the antiderivative to go back to velocity? Absolutely. What if we're at velocity? Can't we take the antiderivative to get back to position? Absolutely. So just realize that this entire concept is the same thing, except we're going to be going in the opposite direction. Okay, so let's read 21. It says, neglecting air resistance, the motion of an object moving vertically near Earth's surface is determined by acceleration due to gravity. Okay, that's got to be important. Which is known to be approximately negative 32 feet per second squared. Just a note on this, you're used to the 9.8, but 9.8 is meters per second squared. You're going to do this problem in the homework or in the lab, I don't remember. So what I did was I converted it to feet per second squared in order to give you an example problem, and it wasn't repetitive. Just a note there. All right, it says, suppose the stone is thrown vertically upward at t equals 0 with velocity 130 feet per second from the edge of a cliff that is 300 feet above a river. Okay, so what do we need to do? We basically need to find, in our first step, the velocity. So in order to find the velocity of an object, we basically have to take the antiderivative of, remember, to go backwards, the antiderivative of the acceleration dt. Okay, that is the focus of this. So what did they give you the acceleration in this problem? Well, they said it was due to gravity acceleration, and then it was this negative 32. So that's weird. Why is that weird, students? Because the actual value that we're taking the antiderivative of is a constant. Now, you've done this before, but you've usually done it at the end of polynomials. It was actually in the beginning of the section. So what happens when you do this? Well, the negative 32 goes to the front, and we're just taking the antiderivative of basically 1. Well, what is 1? 1 is just t to the 0. So if you take the antiderivative of t to the 0, you get t to the 1 over 1, which is just t. So therefore, what do we get? We get negative 32t plus c as our velocity function. Okay, so hopefully everybody is seeing that right now, this is literally the same thing that we just did, right? So the only thing we need is initial condition. So that is what this was about. So our initial condition in this problem basically stated that the velocity was 130 feet per second at time is equal to 0. So in other words, if we were to write that out, we're saying that, oops, that is a highlighter. We're saying that, I'll do it in a different color, v of 0 is equal to 130. Okay, that is the main thing here. So if that's the case, then we can go over here and go, okay, 130 is equal to negative 32 times 0 plus c, which means c is equal to 130. We can then return to our equation and write v of t is equal to negative 32t plus 130. So we can basically take this right here, this guy, and put it in for c. So this is essentially the answer to our problem. V of t is equal to negative 32 plus 130 for this specific problem. Okay, so what if they took it a step further and they said, now, let's see if you know what you're doing. Let's find the position function of the object. Okay, well, again, if you're given the velocity, then you should be able to take the antiderivative to get the position. All right, so position should be equal to the antiderivative of v of t dt. Well, guess what? Didn't we find that right here? We did. So let's put it in there. So we're going to get negative 32t plus 130 dt. Alrighty, so where do we go from there? Well, this is a more typical problem to take the antiderivative of. So we have a constant negative 32. What's the antiderivative of t? It's t squared over 2, right? Then we have a constant of 130. What's the antiderivative of essentially 1? It's going to be just t. So the antiderivative of 130 is 130t, right? Plus c. So this is essentially our family of position functions. So let's simplify. So we're going to get negative 16t squared plus 130t plus c. Okay, so just like we did before, again, we now, if you look at our initial problem setup here, not only was the velocity 130 at time 0, but we were 300 feet above the river. That's actually the initial position. So s of 0 is actually equal to 300. So just if you want to note this, this is the initial condition for velocity. And this is the initial condition for position. Say that a lot of times fast. Position. All right. So if it's s of 0 is 300, then 300 is equal to negative 16 0 squared plus 130 times 0 plus c, which means c is 300 again because these all wipe out. So if we were to rewrite the answer, it would be s of t is equal to negative 16t squared plus 130t plus 300. And this is our position function for our problem. Now, just a side note, these are the answers, of course. What students do, what you want to be careful that you do not do, is that, see this step right here in both problems? Hold on one second. So let me do super colors here. So see this step right here, and here, going from this to this. So what students do is they go, oh, so the initial condition will always create a c of whatever your condition is. So look what happened. So what was the initial velocity condition? 130. What did c become? 130. What was the initial feet above the river? 300. What did the c become? 300. Why did that happen? That only happened because our function was a polynomial. It will happen with a polynomial all the time. But if I give you some problems where you end up with a different, let's say, some condition within another function in it, especially trig or even exponentials, that actually is not going to happen. So do the work either way. Do not take shortcuts because you're going to sell yourself down the river, so to speak. If you do that, just do the work and get to the result, and that'll be good for you.